Question 11. What does GPS stand for? Is it Global Pathfinding Satellite, Global Pinpointing Satellite, Global Positioning Satellite, or Global Positioning System? Well, we have a few options, so let's go through them. Let's start off with A, Global Pathfinding Satellite. Now we know that we can use GPS in order to figure out the route from one place to another place, but GPS won't do that on its own. We need to combine the GPS data with a computer that has a map of where we are. The GPS simply tells us our location on that map. B says Global Pinpointing Satellite. Now this seems a bit closer, because we can use trilateration to pinpoint our exact location on the Earth. But pinpointing isn't really a particularly scientific way of saying things, so I think we'll let it go for the moment. How about C, Global Positioning Satellite? This is the closest one yet. Positioning seems like a pretty scientific word. The problem is, the S of GPS does not stand for satellite. It consists of a whole bunch of satellites orbiting the Earth. That's not a single satellite, that's 24 different satellites. So it's not just a satellite, it's a system of satellites. So GPS stands for Global Positioning System, and D is the right answer. The system will use satellites to pinpoint the position of an object on the surface of the Earth, and then we can find paths to it by using appropriate maps and technology. Question 12. What sort of electromagnetic wave do GPS satellites emit? We have ultraviolet light, visible light, infrared light, or microwaves. Now we know from our study on electromagnetic waves that the sun produces most of these, but a lot of them get blocked by the atmosphere. The three brightest wavelengths that get through are ultraviolet light, visible light, and infrared light. So because these are emitted by the sun and are so bright, any signals emitted by a satellite in these wavelengths would get swamped out pretty fast. So for this reason, we use microwaves, that is, very short wavelength radio waves, to transmit data. Question 13. It takes a very small amount of time for a certain GPS satellite signal to reach its receiver. Calculate the distance between the satellite and receiver. Can you remember how we do this? Well, it's simply distance equals speed times time. So we have a speed, 3 times 10 to the 8, the speed of light, times time, 0.075 seconds, to end up with an answer of 2.25 times 10 to the 7 meters, or 22,500 kilometers. This is how far away the satellite is. Part B. If the satellite's clock is off by 1 millisecond, that is 1,000th of a second, what difference will it make to the answer? Well, to find the answer to this question, all we need to do is take the change in time, that is 0.001, and multiply it by the speed. Surely 1 millisecond couldn't throw the estimate off very much, could it? Let's find out. What we do, we take 0.01 seconds, multiply it by the speed of light, and we'll end up with an answer of 3 times 10 to the 5 meters. That's not very much, is it? Well, if we convert it to kilometers, we can see that it's actually 300 kilometers. So it does make a fair amount of difference to where the GPS thinks you are. This is why it's so important to have such accurate clock on board the GPS systems, GPS satellites rather. If they're off by even a tiny amount, then we can get huge error in the prediction of our locations. Question 14. Suppose it's possible to use any sort of satellites to calculate a position. Is it possible to calculate the receiver's location using any 3 satellites, if we can look at any satellite in the sky at all? And explain why or why not. Now I mentioned before that if we have 3 circles, and they all overlap at a common point, then we know that that point must be where the GPS receiver is. It looks like as long as we have 3 satellites of any distance from us, we should be able to tell where we are. But that's not quite true. Supposing that instead of those 3 satellites, we had 2 satellites that were directly above the same spot on Earth. We might have one in a very low Earth orbit, or we might have another one very far away, but at the same spot, right? Just higher up into space. And then we have a 3rd satellite over here. The 3rd satellite will draw the circle, just as we expect, but both of these first 2 satellites will draw circles that are pretty much identical. And that gives us a problem. We can't tell the difference between these circles well enough to figure out whether we're at this top point or this bottom point. One of these lines will represent the overlap accurately, one of them won't, but the thing is the circles are so similar that we can't actually tell the difference between them. So we need to make a bit of an addendum to how trilateration works. We can't just use any 3 satellites. If we have 2 satellites that are over exactly the same location on the Earth's surface, then we won't be able to get this to work. What we need to have is 3 different satellites that are at different locations on the Earth's surface. And as long as we satisfy that criteria, we should be able to get the trilateration working properly. Finally, question 15. If a GPS receiver is on the Earth's surface, it needs exactly 3 satellites to ascertain exactly where it is. But if it's floating in deep space, it doesn't need 3, it needs a different number. So what is this number? Well, let's think about this for a moment. When we're on the surface of the Earth, then one satellite gives us a circle of possibilities on the surface. But if we're in deep space and we know our distance from a satellite, that means that we could be that distance away from the satellite in any direction. We could be in a sphere around that satellite. So if the receiver knows its distance to the satellite, we end up with a sphere of possibilities. Now if we have 2 satellites, then that's 2 spheres, and they're going to have to overlap each other. So what we have is 2 spheres overlapping. They'll have this little boundary of intersection. One part of the intersection is on the front, one's on the back. And so we end up with a circle of possibilities where the spheres cross over. Now this looks a little bit like our circle of possibilities on Earth, because remember with Earth, we have the one sphere that we're standing on, and we know our distance to the center of the Earth. So knowing the distance from another object, in this case a satellite, gives us a circle of possibilities. So what we need is just one more sphere than in the 2-dimensional case on the surface. So the second sphere will overlap with the first sphere and create a circle of possibilities. A third sphere will create 2 possible points, and a fourth sphere will determine which of those 2 possible points is correct. So that's the end of the questions, which means we're at the end of the section, and almost the end of the module. So in this section we've learned about GPS, we've learned about exactly how it works and how trilateration works, and how we can use the distance between 3 different satellites to ascertain our exact location on the surface of the Earth.